Good morning, ladies and gentlemen. My name is... Good afternoon. You know, I come from Bordeaux, and in Bordeaux, usually, we wake up very, very late. I apologize. So, my name is Eric Rivel. I'm working in the field of signal processing, and as I told you, I'm working in Bordeaux, a very nice place. So you are all welcome, of course, in Bordeaux, and we'll probably organize many conferences in the future. So today I'm going to present you a work that I did with one of my PhD students. His name is Léo Legrand. This is not necessarily the core of his PhD, but today we are going, in fact, to focus our attention on process comparison based on Jeffreys divergence. As you know, several measures exist to compare processes, and we can either look at spectral distance measures on the one hand, and on the other hand, we can take advantage of general distance measures, and of course, several experts in the field contributed to this area, from Pearson to Rennie, and of course in the last decades there were also many works dealing with alpha divergences, F divergences, and when comparing more than several probability distribution function, F dissimilarities. Of course, and as it was told today, divergences and distance are used in a wide range of applications, from texture classifications to biomedical signal analysis. And in this presentation, we are going to focus our attentions on Jeffreys divergence, which is the symmetric version of the Kullback-Leibler divergence. And in fact, our purpose is to compare random processes such as autoregressive or moving average processes by using Jeffreys divergence. We did several studies on it for the last years, and here is the summary of the previous works we did on it. As a matter of fact, the Jeffreys divergence tends to a stationary regime when the number of variates increases. And if we call the difference between two consecutive GDs that are computed with k or k minus 1 successive variates, in fact we can deduce the so-called asymptotic Jeffreys divergence increment that can be useful to compare the random processes. In this case, in fact, we don't have to select the number of variates, which can be quite difficult, especially because when we look at the way the GD evolve, in fact, there is a transition period before converging to an asymptotic, in fact, increment. And so this increment can be useful to compare random processes. We try, in fact, to give an interpretation of this asymptotic increment, and it can be seen as a way, in fact, as autoregressive and moving average process can be seen as the filtering of white noises. In fact, this asymptotic GD increment can be expressed from the power of the first process filtered by the inverse filters of the second process, and conversely. So it can be very funny to see this interpretation, because in this case we can understand, in fact, the value we can obtain from this asymptotic GD increment. There is also some extension that can be, of course, obtained with long memory processes, and especially fractionally integrated white noises and RFIMA processes. And so that can be useful in other areas, such as financial and many other top fields. Nevertheless, interpreting the value of the asymptotic GD increment is not necessarily an easy task, because we take into account all the parameters. That means the autoregressive or moving average parameter, the variance of the driving processes. And we saw that, as a matter of fact, it was quite difficult to compare this, and we could have very strange values, and it was very difficult. This is the reason why we just suggest to compare unit power processes, because in real application from data we can always estimate the power, so we can deduce in fact unit power processes. And on the one hand, the idea is to compare the unit power processes. This makes it in fact possible to get rid of the variance of the driving processes. And on the other hand, we just have to look at the ratio between the power processes. So let's just define very quickly, as you may know, the Kullback-Leibler divergence. So in the Gaussian case, we can obtain this expression for k variates. And for the Jeffreys divergence, as it is the symmetric version, we have a very nice expression that only depends on the covariance matrices, and there is no longer any influence of the logarithm, for instance. So the question is then just to compute and to have expression of these covariance matrices. Concerning the asymptotic GD increment, the idea is so to compute two consecutive GD, to look at the increment, and then to analyze how this increment evolve, and to see what we obtain. So this is the so-called asymptotic GD increment. So if we look at it, in fact, in previous work, we showed that this corresponds, as I told you, to the power of the process X, the first, that has been filtered by the inverse filters. And conversely, this is the second term corresponds to the power of the process Y that has been filtered by the inverse filtered associated to the process X. So now the idea is to simplify the interpretation, and so I'm going just to give you a very simple example. If we take into account the GD between an autoregressive process, a first-order autoregressive process, and a white noise, and if we look at the asymptotic increment, it can be shown that, in fact, this asymptotic GD increment depends on the variance of the driving processes, which are denoted sigma square U1 and sigma square U2, and the AR parameter of the AR process. So there are various influences, in fact, here, due to the power of the driving processes and the AR parameters. As a consequence, the Jeffreys divergence, in this case, the idea has been to look at the value of the asymptotic GD increment by taking into account several values of the AR parameter on the one hand, and on the relative difference between the noise variance, and to see how the GD could evolve. And with this type of expression, we can say that, in fact, depending on the value, we can obtain the same type of value, and so it depends, in fact, on two parameters. Once we have normalized, the expression only depends on the AR parameters, and we have been able to get rid of the variance of the driving processes. And so in this case, we can just look at the asymptotic GD, and we can see that it only depends on the AR parameter. Another example, in this case, we compare two autoregressive processes defined by their AR parameter and the variance of the driving processes. In this case, the asymptotic GD increment depends on the AR parameter, the variance of the driving processes. So there are several parameters that have an influence on the GD, and so it is quite difficult to interpret or to have an idea of the type of value we can have. So here are some examples. You can see that the ratio between the variance, the ratio between the variance of the driving processes has in fact an influence of the shape on the GD when we try, in fact, to make the AR parameter vary in the interval -1, 1. You can see that we have, in fact, different type of shapes. This is the reason why, by comparing unit power processes, as a matter of fact, the expression no longer depends on the variance of the driving processes, and we have a single shape that makes it possible for us to simplify, in fact, the analysis of the GD. So, in fact, our purpose was to be able to interpret the value of the asymptotic Jeffreys divergence increment and to be able to use it in practical case. It is true that on the one hand the theory is of real interest, but on the other hand, in practical case, when we have some data, we want to model them, then we want to compare some data, it can become quite difficult to choose the type of parameters, and several things have an influence of the Jeffreys divergence. And so our purpose in this type of work is to also make connection with spectral analysis on the data. Okay, thank you for your attention.
Questions?
I have a very stupid question. What is the power of the process?
The power of the process for an autoregressive process? It is for first order. For first order, it's just sigma u squared, the variance of the driving process, divided by I1 minus the autoregressive parameter, the square of the autoregressive parameter.
And if it's not order one?
Then you have it can be expressed from the AR parameters. The simple case is.
What does it represent?
Sorry?
What does it represent?
The power of the processes. In fact, in signal processing, you have when you have small amplitudes of a signal, you have a small power. When you have large amplitude, you have a large power. So it means that depending on the data you may have, some data may have small amplitudes, so may have a small power. Other may have large amplitudes, they may have a large power. As a consequence, comparing, if then you try to assign a model to this data and you try to compare them, necessarily, at the very beginning, there is a problem because they don't have necessarily the same power. And so the GD can be very high due to this fact. And then the autoregressive parameter has an influence of the spectral shape. The driving process has just an influence on the way the spectrum is, in fact, but you can adjust it. I don't know whether I'm clear or not.
Other remarks, questions?
For my own curiosity, because I went formerly at the corporate level of Thales research, I'm going to understand what is the role of your training in this.
As a matter of fact, Leo is just working in the field of tracking. And at the very beginning, as you may know, when we are working on object tracking, we can play with approach based on Bayesian solutions such as Kalman filtering, particle filtering. And when dealing with objects that can move with different motion, then we can develop multiple model algorithm based on different type of modeling. And one point is that one assumption, strong assumption, is to have dissimilar models in order to be able to cover all the situation. So the very starting point of our work was to be able to compare motion models and to be able to see if we could have some dissimilar motion models. And as when I was younger, I worked a lot on autoregressive process, moving average process, and so on, and I found it very funny, in fact, to see what happens if I wanted to compare data model by autoregressive model, moving average model, fractionally integrated white noises, and so on. And so he's working on this topic, but as he's very, he has a strong will to learn, then he spends additional time on this type of work.
Other questions for now? Just one.
So,
Oh, excuse me.
So Jeffrey's divergence is often very unstable because it can go very quickly because it's not bounded divergence.
Yeah. This
Did
is the reason why we don't use we don't use the Jeffreys divergence. We work and we look at the increment. And it is true that, as you may know, when dealing with moving average process, for instance, if as we know that the increment corresponds to the inverse filtering of one process, and conversely, if a moving average has zeros on the spectrum, the inverse will have infinity. As a consequence, the increment goes to infinity also. And so it's a way sometimes to detect when we have, in fact, zeros in the spectrum. And for fractionally integrated white noise, it's also a way to see the order of differencing if the order between two fractionally integrated white noise is higher than 0.5. In this case, the GD and the increment goes to infinity. We had this problem, in fact, because of course you are totally right.
This can also be the family that interpolate between Jeffrey's divergence and essential. It's one parameter family that can interpolate into July.
Okay, we can discuss. Thank you very much.
Other remark? Just maybe one thing. This seems related to the Gaussian property of those processes using the pullback because of the simplicity.
As a matter of fact, we are quite lucky here because due to the Gaussian nature of the processes, in this case, the expression of the Kullback labor or the expression of the... But there are some recent work dealing with non-Gaussian processes and Jeffrey's divergence. And so we are currently starting some discussion with the colleagues working on this field.
Because this seems that, for example, for heavy-paid processes, we can take autoregressive with student noise, for example, or those kinds of things. So maybe divergences, as the Rayleigh type of divergences or power type divergences, may have some possibility to somehow adapt to heavy paid. The interesting and difficult case would be to compare processes with different kinds of paid properties.
I totally agree. But it's true that as it is not necessarily the core of our research, we go step by step. But there are so many things to do, and it's very interesting in any case. Thank you.
So thank you very much for this talk.